Yes, thank you. So I'm Colin DeGraf, and I'll be talking about using simulations to look at how black holes cluster between low and high redshift and what we can learn about the black holes and their hosts. So I'll start with a quick summary of the simulation, and then I'll go into discussing how the black holes actually cluster and how luminosity dependencies play a role there. And then I'll move into links with host halos, and particularly the host mass of those halos. We've already seen a little bit of how the black holes are related to their host galaxies, so here I'll talk about that. And then what that means for estimating duty cycles coming from clustering information. So the work I'm doing is using the Illustris simulations, which I assume people have heard about before, but it's a 100 megaparsec box using the moving mesh Coda repo. It includes many of the typical physical models you would expect to find in cosmological simulations. And we have a minimum cell size of about 50 parsecs that gives us a gas mass of about 10 to the 6 solar masses. I don't want to go into too much detail for the simulation, but what's relevant for this talk is how the black holes are treated. So this isn't trying to resolve the formation of supermassive black hole seeds, so we simply insert black hole seeds into any halo that's sufficiently massive that doesn't already have a black hole in it. Once black hole's been inserted, you grow using a Bondi-like formalism that has an additional pressure criterion to decrease the accretion rate if the pressure is too low to compress the gas down onto the black hole. And then there are 3 different types of feedback for the black hole. At high accretion rates, you have quasar mode, that's just an isotropic thermal feedback. At intermediate levels, you have radio mode where you're inflating bubbles. It's supposed to be, so if you have a radio jet, it would inflate these radio cavities nearby. And there's also a modification to photoionization and photoheating to account for radiative feedback. So these simulations have been used to reproduce many different properties of black holes and matched with observations. Here's an example from the main Illustris black hole paper, just showing the scaling relation and how it does a good job throughout. What's relevant for this talk, however, is looking at black hole clustering. So here's an example of the correlation function for black holes at redshift 0 in Illustris. So the gray shaded region shows us how much it varies between 5 sequential snapshots. So at the very small scales, we have a little bit of variation, but at any sort of physical separation that we're interested in, we're extremely well converged between snapshots, and we average across them anyway, just to be safe. So then we can split the correlation function up into 1 and 2 halo terms. So in red, you're just seeing what's happening of clustering of black holes in different halos, and in blue, you're seeing the clustering of black holes within individual halos. So you can see that these halos at redshift 0 typically have a characteristic size of about a megaparsec. So when we're looking at any information that we're trying to correlate with host properties, we only look at larger scales, so we're not biased by the small scale clustering. And then you can compare that clustering to dark matter, and at redshift 0 anyway, it's very similar. And then on top of that, there's another curve there that's showing how galaxies are clustering. So redshift 0, all of these things are matching each other very closely. But then you want to see how how this evolves over time. So you can see here several different redshifts. So as you go from low redshift to high redshift, you can see the bias of black hole clustering, halo clustering, and galaxy clustering all changes quite significantly relative to the way dark matter clusters. And so that's one of the things that we're going to compare quite often here. So then to try and characterize what kind of luminosity dependencies we have, this is showing the ratio of a luminosity selected correlation function to the entire black hole sample. So you can see at at large scales at redshift 0, there's really no luminosity dependence that we're finding. If you're talking about within one halo, then you do start to find a bias. So that has to do with the fact that if the halo is able to fuel one black hole, then it may be able to fuel multiple if they're all found there. If you compare that to higher redshift, however, this is redshift 1, then you start to see that even in the 2 halo term, when you're talking about more than megaparsec scales, you do have a luminosity dependence, and the more luminous black holes are clustering more strongly than the less luminous ones. And that's that's happening out at the 2 halo term, but again, within a halo you see much stronger evidence for that. So here you can see it across all redshifts, well, from 0 to 4 anyway. So you can see at low redshift and at high redshift, you tend not to have a lot of luminosity dependence with in the 2 halo term. But at the intermediate redshift you do, that's where you have the most luminosity dependence. It's always evolving there. So another way to just show that rather simply is define the correlation length and then see how that evolves with time. So here you have correlation length for different AGN luminosity selected samples. And so you can see there's actually not that much redshift evolution for the correlation length, especially for the high luminosity samples. It's quite smooth. If you compare that, here's the way the correlation length for dark matter evolves with time. You've got a noticeable difference. Then if we overplot on top of that how galaxies evolve, the correlation length for galaxies, you can see at high redshift, this matches the AGN samples quite well, which suggests that these AGN are found in these sorts of galaxies and evolving together with the galaxies. Below redshift of about 2, however, it diverges quite strongly. So at that point, the AGN are doing one of 2 things. They either have to be being found in larger halos at low redshift, or they have to be found in biased halos. And we find out it's actually both, which work together to produce this result. So to compare with observational data to see how well the simulation actually does, here's a whole bunch of different surveys that have been done, correlation lengths for AGN. So you can see as you start getting to high redshift, we don't have as good agreement. But a lot of that is because of the luminosity thresholds. This simulation is 100 megaparsecs. We don't produce the very, very luminous quasars that a lot of these measurements are taking into consideration, and especially as you go to higher redshift. So if we account for the luminosity evolution, then we bring down the observational data. This is using a luminosity-dependent clustering formalism that's been recently proposed. It's highly uncertain, but it's a reasonable approximation. It does seem to match our simulation. And that shows that then we start to match quite well. So now these are all supposed to match this blue line in terms of the luminosity sample. So we do a pretty good job of matching the data. And you can see the same thing if you, instead of look at correlation length, you look at the bias of the black hole clustering relative to the dark matter. And again, once you get to the very high redshifts, we start to diverge a bit more. But the agreement is still generally quite good, especially given how uncertain those high redshift observations are. So having considered that the clustering does pretty good, then we want to see what does the clustering suggest to us about typical host halo masses. So these curves show us the actual mean host halo mass in the simulation for different black hole luminosities. So that's just what we get if we explicitly select. Do you have a question? Okay. We'll get to it then. So here we've got the evolution of the typical host halo mass. You can see it does grow with time. As you get to lower redshift, they're typically found in more massive halos. These dotted lines are showing sort of the median expected halo growth rates. And you can see it doesn't match the actual halos in our sample. So the reason for that is at very high redshift, you're tending to have new black holes that are just barely starting to cross these thresholds. So the evolution of the typical host halo mass doesn't evolve as significantly, because you're always getting new black holes in smaller halos that somewhat counteracts that. At low redshift, you actually have the reverse process happening. So the black holes in the smaller halos start being quenched, and they're no longer bright enough to fit into this. And so you start losing them, and you're only left with the more massive halos. And that also means you're biasing your clustering a bit, simply because you're selecting the halos that have a better gas supply to fuel these black holes. So we're finding that in general, the typical host halo masses aren't evolving like a typical halo does, because of the way the black holes actually occupy halos differently at high and low redshifts. Now the problem with this is, what happens if you try and estimate the host halo mass using the clustering data? And so that's now shown in these dashed lines. So essentially I'm just taking how strongly clustered the black holes are and using only that information to try and predict what the typical host halo mass is, which is often done with observational data. And you can see at very high redshift we do quite well. But at lower redshift, we start to diverge moderately. And this is using only central black holes. If you allow yourself to consider satellite black holes, the agreement is much worse. So what we're finding is at low redshift, the black holes are clustering more strongly than their typical host halos. And that gives you this bias, which then sort of snowballs when you're trying to use that information to make other predictions. So to see why that's happening, this is the distribution of host halo masses for black holes at redshift 0 and 4 and for 2 different luminosity cuts. So you can see it's reasonably wide distribution, but at low redshift, it's a much wider spread. So that dot dashed line is the actual mean host halo mass in the simulation. The blue one is now what we would predict the mean is using only clustering data. So at high redshift, it's essentially perfect, but at low redshift, you start to diverge. And that becomes more problematic if you try and use the clustering information to estimate the minimum mass you would expect to find one of these black holes in. And so the red line there is the minimum predicted mass from this formula for where we would expect to find these black holes. And you can see this is very far from the minimum mass where we're actually finding these things. So you really need to consider how much of this low mass tail really exists when you're trying to make any estimates. And part of the reason for that is the way the Eddington ratios evolve. At low redshift, you have this black line. This is just the distribution of Eddington ratios. So at low redshift, you have this high-end tail, and that then corresponds to an unexpectedly low mass hosts because they have very high mass, very high Eddington fractions. So we really need to see those differences. And that becomes most important when you try and estimate duty cycles. So we've already heard a little bit about black hole duty cycles. Here I'm defining a duty cycle. It's just the fraction of black holes that are above a given luminosity cut. And so you can see for different luminosity cuts, the evolution with redshift is quite smooth. It's quite nice. The one exception is the very luminous, very high redshift sample, but that's just because we have an imposed Eddington limit. So we don't have enough massive black holes in our volume to be able to produce high fractions. So if you do a cut on Eddington fraction instead of luminosity, you see it's all very nice and smooth. So we have nicely evolving duty cycles with redshift. But you can't get this information observationally because this would require knowing how many black holes there are that are not active. So we try and consider a comparison to what you would typically do to use observational data. Here's our actual black hole duty cycles, just the fraction of black holes which are active. If we compare that to a fraction of halos above a given halo mass, where that halo mass is the halo mass above which we find at least 99% of our black holes, high redshift it does okay, but at low redshift it diverges significantly. And that's because of the way these black holes are clustered. We can do a much better job if we just use a fixed halo threshold. So in fact, the best number we can get is if you use a fixed halo mass of above 10 to the 11.2 solar masses, it evolves extremely well across all redshifts. But where this becomes most problematic is, again, if you try and predict this using clustering. So the way people will do that is based on your luminosity choice and luminosity function and the halo mass function above some minimum mass. So if we use that minimum mass that we found in the clustering, then we get this duty cycle, which is clearly dramatically wrong if you compare that to the solid lines here. It's mostly at low redshift. And again, that's because at low redshift, you do find a lot of these black holes in very low mass halos that you might not expect. And so you have to take that into consideration. So this is using all black holes. We can partially fix that if we only consider central black holes and we don't consider satellites at all. But even so, you still have at low redshift this dramatic increase with low redshift. So any sort of duty cycle estimate that you're doing observationally, you can't just limit yourself to the typical masses you would expect based on the clustering, because at low redshift, these black holes tend to cluster more strongly than their typical host mass might predict. So to summarize, these simulations do a very good job of matching up observational data for black hole clustering. And you can see that if you then try and use that information to make estimates for the host halos, you really need to take into consideration the fact that you do have a wide distribution of typical host halo masses, and any sort of estimate you use straight from that is actually going to be more accurate at high redshift than low redshift, just because of the way these distributions work. Thank you.
All right, questions?
So Illustris has a mass threshold beyond which you assume all halos have a black hole, yes?
Yes.
How sensitive are these results to that mass threshold? Do you have an idea of that?
Depends which results you're talking about. In general, the higher luminosity cuts you consider, the less sensitive it is to that threshold, because the more luminous things, they have to have grown to be much more massive. So what I have done for all of this work is I never consider any black holes below 10 to the 6 solar masses. So I've cut out any black holes that are only recently seeded. They have to have grown by a factor of a few before we even consider it. I've also tested using higher mass thresholds for that, and it doesn't tend to have too much of an effect. You do start to have a little bit of a bias on some of this. You can shift that a little bit vertically, but qualitatively it's really the same regardless of how you seed.
Other question? Yeah. You can go ahead and sit up. Yeah.
Black holes.
Yes.
Keep moving. That's correlation length, correlation function.
Oh, sorry.
So black holes live in halos with about 10 to the 12, 10 to the 13 and above, right? And you're saying they're not biased.
And I say
Looking at the curve, correlation function of black holes, which is a full line, right, and correlation function of dark matter are basically one-on-one, which means that your correlation function of black holes, which are living in 10 to the 13 halos or 10 to the 12 halos, are not biased. And it's not strange to you because they should be like biased by factor of, let's see, in correlation function by factor of 4.
So this is, I mean, that's only redshift 0 as you go to higher.
At redshift 0. I'm looking at redshift 0.
This is selecting galaxies, not halos. So it's based
No,
on
doesn't matter.
You're
selecting your black holes, which live in halos of 10 to the 12, 10 to the 13 solar mass. Is it true? About, right?
And lower mass. They go down to below 10 to the 11 solar mass halos.
And so that population of black holes is basically unbiased, and you say that it's normal.
Yes.
Isn't that strange? Because those should be biased. You're selecting relatively massive galaxies, and mostly of them would be in 10 to the 12. So most of yours still should be at the 10 to the 10 solar mass halos, which is kind of strange.
In this figure, yes, because in this figure, this isn't using any sort of luminosity cut. So
no, it doesn't matter. This is a selection of black holes. We know where they live in massive halos, right? And most of yours is at 10 to the 10 halos, and which is unbiased, which is
well,
bizarre.
yeah, because you're seeding into 10 to the 10 solar mass halos. So that's where most of your black holes are if you're not putting in any additional cuts. You have to put in something else. I mean, the black hole mass function, it's always weighted most towards the lowest mass object. So your recently seeded things tend to dominate the results. It's only when you put in the mass cut of 10 to the 6 solar masses, it doesn't do too much in this case. But then also a luminosity cut, that's when you start to parse your sample down a bit, and then you start getting all of your biased results, which all of the rest of the figures do, which is why then the biases start to come out.
I was wondering, for the black holes that are providing a lot of feedback through the radio mode, do you have some kind of observational sample you could do a cross correlation and compare the clustering of the black holes that you think are in the radio mode and the ones observationally that you suspect are the ones in the radio mode?
Yes, so we've looked at some of that. So I didn't include it here. I've done cross-correlation functions between black holes and various galaxies within our sample and looked at some of these separations. It gets a little bit tricky just because you have a hard cutoff between quasar mode and radio mode to get nice results. But maybe I can talk to you a bit more during the break. And I think I have some of those figures on my laptop I can show you.
Okay, so it sounds like lots of interesting discussion for the break. Let's move on. Let's thank our speaker again.